luckily it didn't crash, but she had to dead stick it the whole way in.
Wow.
We used to have those things fly around, test firing runs in basic.
Mm-hmm.
That Vulcan gun is just like,
you cannot tell the individual firing, right?
no, it's just loud.
Is it a Gatling gun?
Vulcan gun.
Okay.
If they would use up their whole payloads, that, like, hey, all they're trying to do is take out a couple of tanks. Just and have them
Well, all fighter pilots will tell you, you don't hold the trigger button. Yeah, there's no way they can do that. They always shoot in pulses.
They go for a while, but when we're on basic, you hear it go like that.
Well, that's because they're not under enemy fire. they don't have to worry about, okay, am I going to run out of ammo on my way back home and encounter hostiles, right? Multi-threading and round robin do not imply preemption. Okay, so we are adding more and more features to the kernel. This is interesting because preemption means if a task or if a thread is saying, okay, I want to get stuck in a big long loop to process a video image, and I don't want to give up control by myself. Preemptive thread change means some mechanism will come in and say, hey, thread number blah blah blah. You have been executing for the past 10 milliseconds already. It's time to give up control. But I don't want it. Okay, I'm taking control away from you anyway. Okay, so that's preemptive. That's the preemption of a thread to basically say, okay, you don't have control anymore. At this point. A good real-time kernel should always allow preemption of threads. Preemption is the act of a real-time kernel forcing a thread to give up processing resources and passing processor resources to the next thread, whoever is available next or at a higher priority or whatnot. This is quite useful for threads that are compute bound, okay, like processing video images using a very slow 8-bit processor. Let us consider our example thread that computes the best path to a destination. Most algorithms for such a task do not have a convenient point to yield. In other words, it's really hard for the designer of the algorithm to say, okay, this is probably a good point to give up control and continue later on. In order for other peer threads to get control, the kernel must force the algorithm to give up control. For any multi-threading implementation using multiple stacks, preemption is relatively easy to add. The easiest way to add preemption is to add logic to use in a timer interrupt surface routine. So we are tying in, a timer ISR into this whole mix here. A timer is basically a hardware device on most processors. What you do is you can just tell the timer and say, give me an interrupt in 1 millisecond. Okay. And then the timer will go off and do its own thing without any further, software manipulation. So, so after 1 millisecond, an interrupt will occur from that timer, and then the operating system will be able to handle that interrupt. So at that point, the operating system can look at the thread, who has been executing for the past millisecond. If it is the same thread that has executed for the past millisecond, and the time limit is set to 1 millisecond, the kernel or the ISR triggering the kernel can basically say, okay, you have to give up control now. So what actually happens at that time is it will save all the registers, save the entire state of the processor onto the stack of the thread being interrupted, okay? And then it will just use a small data structure to represent the thread and put it to the back of a queue, okay, to the back of a circular queue, and then get the next one in, and then say, okay, now you can resume execution. How do you make a thread resume execution? The reverse of what I just talked about. Okay, you resume the stack pointer onto the stack of the thread that is going to be revived, and then you pop all the saved registers along with some other states, and then you move the data structure of that thread from the wait queue back into the front of the queue. And that's it. That's how you switch the context between threads. No, in a nutshell. Okay, so here we have a whole bunch of stuff. This can be done as follows: pushing 2 more bytes on the entry point of the timer ISR. These are really itty-gritty detail of how to get it done. So essentially, you want the timer ISR to return from the interrupt to the yield subroutine and perform 2 actions. First, the return interrupt instruction enables interrupt, and then the new subroutine saves the context and switches to the next thread, which is basically what I just said. Low-level details that you don't have to worry about. Okay, now we have priority queues. Okay, so far what do we have? So far we have the concept of a thread, okay, which means you have subroutines that can execute quote-unquote in parallel to each other. We have round-robin scheduling, which means, of all these threads that are pretending to execute in parallel, you can have each one to voluntarily give up control and say, okay, this is a convenient place for me to give up control, so the next thread, in the round-robin gets to, execute for some time. And then we added preemption, which means if a thread does not want to give up control, guess what? The ISR will kick in and force the thread to give up control. Okay, so far we have added all these concepts, one on top of another one on top of another one. And this is yet another, type of feature that you can add on top of everything that we have talked about. It is called priority queues, which means of all the threads that you execute, you can basically say some threads are more important than others. Okay, so you basically separate your threads by priority. A high priority thread always has priority over a low priority thread, which means if a high priority thread is ready to run and a low priority thread is running at a time, the kernel will kick in and say, guess what, Mr. Low Priority Queue, because of your lower priority, now you have to give a control for the thread that has a higher priority to execute, even if it is not at a time slice. Okay, do you see what I mean? As soon as the reason why a high priority thread is waiting is done, control will resume at a high priority queue and will be removed from a lower priority queue. So this is prioritizing all your threads. So many cheap RTKs real-time kernels do not support round-robin and priority queues together, and some real-time kernels only allow one thread per priority. So what we are looking at is something like this. So if you look at round-robin, you have basically peers. Okay, these are threads that are peers, and they can give up control to each other. The giving up of control can be voluntary using the yield, or it can be forcibly using the ISR. But now you have multiple ranks with priority queues. So you have different levels of these things, and one priority may only have one single task. At some point, this thread, which is at the highest priority, will say, okay, I'm done so far, I'm waiting for a certain thing. Okay, usually it's waiting for a semaphore or something equivalent to a semaphore. Now when this guy is waiting, it's going to free up all the processing resources. So now, these three will get a chance to execute. Now if all of these three are at some point that they have to wait for something else, then these guys will get to execute. Now let's just say that when these guys execute, one guy says, oh, okay, I am the reason why this guy is waiting, and we can do a semaphore operation to tell this guy, hey, by the way, you can now resume execution. As soon as that is done, as soon as the reason why this guy is waiting is no longer a reason, this will resume execution whether this guy is yielding or not, whether it's at the time slice or not. This guy will resume execution as soon as possible. Okay, so this is what we call priority queues, because you're separating your threads into lanes. Each lane is a queue, and then you have multiple queues and multiple lanes to represent different levels of priority. Which also usually means that this guy has a really low latency time. As soon as the reason is waiting is over, it will resume execution within a very short amount of time. So the latency is very controlled. But as you move down the priorities, this guy may have to wait 5 milliseconds, 10 milliseconds, and in many cases it cannot even be guaranteed. But since it's not doing something that is really, really important, it can afford to wait a little bit longer. Okay? Any questions so far about priority queues and how everything relates to each other? Any questions? And then we have time-based scheduling, which is which is basically our sleep function or alarm function. Do you guys still remember the alarm function from a little bit ago? So basically, this guy, the highest priority one, can say, Well, I suppose I can wait another